Hello, everyone. So, last time I left off with a big, ugly equation for how we can determine the molecular orbital energies that are generated by taking two atomic orbitals on two adjacent atoms and mixing them up to get a bond. So, as you may have noticed, we're going to have two solutions. One will generate a bonding, one will generate an anti-bonding. But it is also fairly obvious to see this is not the form of the equation we're going to want to use all the time. But it is worth noting, as a review, we have several key parameters that will end up influencing the energy. First, we have our two Coulomb integrals. So these are essentially can be thought of as the energies of the two atoms involved. Beta is the resonance integral. It's essentially the attraction of the electrons in the bonding or anti-bonding region towards the nuclei. So this is going to be very important as a modulating term. This is also going to be very related to S, which is the overlap integral. This essentially describes how much of the electron density is in this overlap region. And that's pretty much it. So we've got most of our system down to 4 variables. So that said, these 4 variables combine together in, well, let's be honest, quite an ugly equation. So what we're going to be doing is looking at 2 potential systems and what approximations I can use to get kind of an intuitive grasp of what this equation is telling me. So the simplest one will generate a set of solutions that should look vaguely familiar. And that's looking at a homonuclear system. So this is, say, I've got 2 nitrogen atoms right next to each other, 2 carbon atoms right next to each other. We've talked about this system a lot before, but mostly conceptually. Now we're going to throw some energy values on it. And here's the beautiful part if I'm making a bond in between 2 atomic orbitals on adjacent homonuclear atoms. Those orbitals have the same energy, which means that their resonance integrals, their Coulomb integrals are the same thing. So this means that I get to truncate my notation. Alpha A is the same as alpha B is the same as alpha. So I'm just using alpha, substituting it into both of these equations. And now this actually becomes quite nice because now the sum of my 2 alphas just drops down to a single variable. And the same thing here and here. So I get 3 substitutions, and these are 3 of the uglier parts of the equation. So when I substitute in the equation, helps simplify the system, little nicer, not quite as long. Doesn't really change anything much conceptually, just helps shorten our notation. But here's where we can actually pull a couple quick math tricks and simplify the system. So you may notice that there are 2's all over the place. In fact, the only 4 that we have turns out to be inside of a square root anyways. So through a little bit of clever math, we can go ahead and get rid of most of those 2's. And we can also get some of this stuff inside the square root to kind of simplify out. Now, this actually takes a while to work through mathematically, but trust me when I say that the equation actually simplifies fairly quickly. Especially as you may have noticed, as soon as I'm able to combine those alpha terms, that inside of that square root simplifies down real quick, and it's actually quite nice. Especially because, as you may have noticed, this now has me taking a square root of a squared. Again, one of the useful things of when I'm able to combine some of these terms, I'm able to herd them all into a squared term. Now, this ends up being quite nice because those end up annihilating. And more or less what I'll have is an energy evaluation of the system. So the center of my energy term, plus or minus this correction term. Now, it's also worth noting that this is all divided by a term related to the overlap. So this is essentially 1, which we'd hope to be their denominator, dampened by the square of the overlap. Now, here's where we can pull some fun mathematical tricks. So when I'm combining these terms, I can go ahead and play around switching with my pluses and minuses to rearrange my central term and again the square root. But here's the beautiful part. I can then distribute this squared term out into its actual squares. So they have opposite signs, which cancels out all of the S terms. And you're like, why would I do that? Well, here's the beautiful part. Because then I can rearrange this top side. So I get a 1 plus or minus s term over here. And now I have a 1 plus s term and a 1 minus s term on the denominator. So no matter which term I choose up here, I'm going to annihilate something, which means that, well, these three terms look a little bit big, they're going to simplify really quickly as soon as I choose a sign. Now, what this leads us to is actually something quite like, because it gives me an energy that's roughly going to be centered on alpha plus or minus beta, and then times some sort of corrective term that depends upon how closely overlapping my two atomic orbitals are. So let's go ahead and pull out this equation. And again, big emphasis here is I'm going to have alpha, so this will be the center of my energies, which makes sense because this is the energy of my atomic orbitals. And then one energy will go up, one energy will go down. Go figure, I've got two atomic orbitals. Energy should roughly be centered on those, and they'll make to make a bonding and an anti-bonding orbital. And that's more or less what I'm going to have. Two atomic orbitals mix, make a bonding, make an anti-bonding. The bonding orbital will be slightly lower in energy because note that my beta term should be negative. I should have a stabilizing resonance integral. And because of that, I'll have a negative alpha because my orbital energies should be stabilizing. Negative beta gives me an overall negative term. Yes, I know it's a symmetric addition. That's thus the positive. And then again, just like we had when we were dealing with the hydrogen molecule ion, it's all dampened by the overlap. The greater the overlap, the more I have to essentially normalize that energy down. So that is one of the unfortunate bits, but unless the overlap gets really big, this ends up becoming relatively not too important. But it is important to know that it's there, especially for numerical values. But if I've got a bonding orbital, I also have the opposite choice, the anti-bonding, where I'll have a negative term here, positive term here, the two positives cancel out, and all I'm left with is my anti-bonding orbital energy. So now energy still centered on that alpha, so still centered on my Coulomb integral, or the energy of my starting atomic orbital. But now all of that resonance is now destabilizing instead of stabilizing, and the decreased overlap changes my normalization constant as we've seen before. So we end up with two equational forms, and I encourage you to go back to the hydrogen molecule ion, and you're going to see that these equations are fairly similar to what we've seen before. But in terms of big picture concepts, what's really important to note is that, again, our energies are going to be centered on the atomic orbital energies, roughly, and they're going to be driven up and down based on our resonance overlap, and again, then dampened by the overlap integral. So again, really what's going to be driving the energy differences is the extent of the overlap, both from an energetic term and to a lesser extent from the normalization values. So more or less, this gives us exactly what we've seen conceptually when we've been talking about the homonuclear molecular orbitals. This is just nice because it gives us an idea of what this means energetically. Now, this is wonderful for homonuclear systems, but again, one of the real big power of generating our secular equations and their solution, as ugly as it is the fact that I can also use it for heteronuclear systems. So where I've got, say, carbon and nitrogen, who doesn't love some cyanide, nitrogen and oxygen, because good Lord knows that's a popular, and same thing with sulfur and oxygen. These are very popular chemical pollutants for atmospheric. So there's a lot of species that actually do matter, even if we restrict ourselves to dinuclear, let alone extending outwards. But again, we've got a few too many terms to deal with. So if I want to try and solve these by hand, we're going to tend to make some basic assumptions. One of the simplest of which is to use to set our overlap integral to 0. So this is called the zero overlap assumption, or zero overlap approximation. Go figure, you can take a guess as why. And more or less what this is assuming is that I'm still going to have some attractive properties, or repulsive for an antibonding orbitals, of beta, just from the energy terms. But more or less, I'm going to be ignoring the extent of overlap of the actual nuclei. So maybe not the best approximation, but it will qualitatively, and even as a rough numerical estimate, get us pretty close to the real system. So when trying to get an idea of how to order my various orbitals, this can actually be astonishingly useful. And one of the real beautiful parts of this is we're going to watch terms drop like flies, and they fall under two major categories. We have terms like this, which will end up going to 0. So we drop out this term, and this term. But essentially, this next one is part of the second group, which is certain terms that drop to 1, which are almost as good, because this term will drop to 1, and I'll be able to simplify down here. And guess what? My whole denominator drops to 2. So with this one simple assumption, we've dropped down from 1, 2, 3, 4, 5, depending on how you count this, 6, 7, 8 terms, down to a much more reasonable 3. So huge. And we can also end up getting some very useful ideas based on what this ends up telling us. But before that, I'm going to do one or two couple little tweaks. So what you'll notice is that my denominator is now down to 2. So this means that I can take the half of both of the precursor term and this whole plus or minus. So doing this distribution will be hugely advantageous. And it turns out, now that I've simplified these set of terms, especially with the square root on the outside, it's actually possible for me to pull out the sum of my two orbital energies out front, though it does leave a little bit of a mess inside the square root, but not too bad. So this is actually going to be our typical energy description for a zero overlap approximation for pretty much any dinuclear species. Though, as you'll see, this will break down for homonuclear cases because they most certainly don't have zero overlap. And when we do this, what we'll find is my precursor term is going to be the average of my two atomic orbitals. So my energy will be centered upon the average of the two atomic orbitals, which again makes sense. Because if I'm mixing two species, they go up and down, but it's always around a central point. So there's no better central point than the average. Now, the correction of how much higher and lower we go does get a little bit messier. So we have this precursor of the difference in between the two orbital energies, which, as you may notice, is one of the reasons this approximation won't work for homonuclear systems, because this term would go to 0. But as long as that's not true, what this is going to mostly do is actually dampen one of the interior terms. Because what we have is that the plus or minus energy correction is being largely driven by this beta expression. So this is my Coulombic integral. It's the energy from the interaction with the bond, for no better description. And this the energy from this interaction then ends up getting driven up by the difference in the orbital energies. So the more similar my two orbitals are, the larger this term ends up getting. And especially because it's got a little bit of a jump start with a +1, this relationship is really going to drive a lot of our behavior. The better the overlap and the closer together my orbital energies are, the more different my bonding and anti-bonding orbital will be from each other. And we'll make use of this a little bit in the future when we actually start applying when we start plugging in numbers to numerically evaluate some heteronuclear systems. Unfortunately, before we do that, we need to have a good way of describing the value that shows up most everywhere. We need a good way of describing our Coulombic integrals, or our orbital energies. So that's going to be the focus of next time. Turns out, though, it's going to take us through a nice side trip through electronegativities. Till then, Take care and stay healthy.